Yeah. So let's just go through the second question, talking where it asks about fugacity. So this is um chapter 11. The, yeah, this is chapter 11. Where it concerns about fugacity and the fugacity coefficient. So what really is fugacity is, so in a system where you have two phases, say in a system where you have two phases, right? Versus say you have vapor and also liquid. So fugacity really talks about how a phase, a species actually, say you have methane, right? They say you have methane. So fugacity really talks about how a species uh, tends to move towards liquid phase or vapor phase. So when we measure, say we have x and y, um, x being molar fraction for liquid state and y molar fraction for vapor state. So when we multiply fugacity with the yi, so let's say if the value is uh, closer to 1, then what it really means that this species has the tendency to move into liquid state instead of has the tendency to move into vapor state instead of liquid state. So the end product, the final answer should really be f fugacity coefficient times the pressure and times with either x or y, depending on the question really. If they give this 70% mole, most probably it's going to be gas. Gas, yeah, because they didn't really set the initial state of the species, so we assume it to be gas as the initial state. So when we multiply with y, then it really means that um, if the value is the final value of fugacity is closer to 1, then it means that this species has a tendency to be in gaseous state instead of, or vapor state instead of liquid state. So what we really want to determine when we ask to find the fugacity and fugacity coefficient is really, we want to know whether nitrogen or ammonia or these two species, whether they have the tendency to be in liquid or vapor state. So let's just go through the first question. Yeah, for this, really to make your job easier is to construct this table here, these two tables, where we have different values of TC, PC, VC, ZC, W, TR, B, not B1, and BIJ. So I meaning when we really talk about, say when we have X, when we really talk about BI or anything really, when we talk about TI or PI, it really means I resembles a species, and J meaning that we have species I and species J. So when I say, oh, what is the pressure I, so that means I'm referring to what is the pressure for the first species. Or if I say what is PJ, then I'm referring to what is the pressure for the second species, the species being nitrogen or ammonia. So let's just go through this. You can really find this in the thermodynamic properties in the table. I feel like I don't really have to specify which table, you guys would know. So just for me, I will list out every details, especially, and I think this table, these values are really in the table, so you just have to extract it, which is WI, TCI, PCI, ZCI, and VCI. Okay, so here comes, I think, the confusing part, because there is so many letters and numbers. So when I say, when we want to find, actually the final equation that you really want is this one. Can you guys see this? The final equation is this one and this one, because at the end of the day, we really want this fugacity coefficient. So these are the equation, which is B11 y2 squared, and delta 1 2. Yeah. I think these are the equations that you really want to highlight in your textbook, which are this and this and this. This one doesn't really matter because it's multi-component, which is maybe more than 2 species, but as far as I know, the questions that I've gone through, they don't really have more than 2 species. So this one doesn't really matter, honestly. We just really focus on these two, because at most we are doing is just 2 species. So yeah, first you want to extract TCIJ. When I say T11, when I say a species of T11, it really means temperature of the first species, because 1 to 1 is just 1, right? So it's just actually 2 1. It's just actually just T1, which is temperature of the first species, and T22 is actually just, well, T2, and T12 is the combined temperature of species 1 and 2. So yeah, before this, when we go through the enthalpy, a system, when we want to combine a critical temperature, what we do is y1 t plus y2 t, right? But for this fugacity coefficient, it's kind of weird because you have a specific formula for combined temperature. Actually, every combined thermodynamic properties for fugacity coefficient has different formula, which is for the first part, TCIJ is TC1 TC2 power 1 over 2 1 minus KIJ. So one important note is that if you have to pay attention to this part. Set all KIJ as 0. Yeah. I don't really feel like explaining what is KIJ, so I'll just skip it. So, but if the question doesn't mention what is the value of KIJ, it is really safe to assume KIJ as 0 if the question doesn't state. So yeah, and other than that, it's just a matter of just plugging in the formula. So TCIJ for 1 1 is just TC1, TCIJ for 2 2, which is actually when you extract it, when you multiply this thing, and not really multiply, this is actually, this value here is actually TC22, where IJ represents I2 and TCII represents TC11, or TCJJ represents TC2. Yeah. So this part of this table here, 1 1 and 2 2, you can just paste it back from here. And TC12 is where TC12 up to W12 is where you want to really use this formula here. Once you have found it already, next is you have to plug in this table. Actually, I can just combine this table, but since the flow of calculation are not really aligned, like I can't really find this value immediately after I find this value. So this value here, TRIJ is just, well, reduced temperature is just T over TC. So TRIJ for 1 1 is just T over TC, and this one here, 1 2, you have to use this TC. So what is the temperature? So 323 over TC 12, which is 226.27. Yeah. And then, actually on that note, actually it's not T over TC, sorry, my bad. You have to use this TCIJ equals to, sorry, my bad. TR12 is equals to TR1 TR2 1 over 2 1 minus K12. Let me just try if I can get the value 323 over 226. Is this 226? 226.27. Or 2.56 times 796 power 1 over 2. Oh, honestly, oh, you know what? Honestly, you can just do T over TC12. They both produce the same result. Yeah, these two are equal. Actually, yeah, it's just the final decimal places are different a bit, but uh, it's up to you whether you want to choose which equation. And B naught is this one. This B naught is 0.083 minus 0.422 over TR 1.6, and B1 is the same thing. Yeah. So use TR for 1 2, use TR 1 2, and for B1 use TR 1 2 also. And for Bij you have a specific formula, which is this one. So just pay attention to that. Bij, yeah, use this one. So if I want to find, say I want to find B11, then it's just RTC11 over PC11 B01 plus W11 B1. Yeah, depending on which species you want to find. And then after you complete this table, you move on to delta 12. Delta 12, we have a specific formula for that, which is 2B12 minus B11 minus B22. So 2B12 minus B11 minus B22. So you see how your life is so much easier when you have this table, because then you don't have to go through all these equations, and you can just refer this table to get your value, and then you get your delta 12. After you get your delta 12, then you can find the ln phi 1. Just plugging in the formula where y2 here represents molar fraction for second species. Yeah. And then after you find the phi 1, actually this value is not 1, it's actually 0.999 something. It's actually, maybe I made a mistake here. You shouldn't really round it off to 1. You are supposed to leave it as decimal, no matter how close it is to 1. You can't really round it off to 1. So just leave it as 0.9 something. After you find that, you times with the molar fraction. So it's actually the proper formula is F1 Phi1 P Y1, and you get 0.14 bar, and here you get 0.059999. Yeah. So if the both F1 and 2 is 0.2, then what it really means that these both species really have the tendency to be in liquid state instead of vapor state, since it's not close to 1 for molar fraction for vapor. So if in vapor form, in vapor state is if in vapor state the fugacity is 0.2, and if in liquid state the F is 0.8. So vapor state, because I use Y, right? If liquid state, I use X. So if in vapor state the fugacity is 0.2, so it does not have the tendency to be in vapor. But if in liquid state it has fugacity of 0.8, it means that these two species really have the tendency to move towards being liquid. Next is B. Assuming the mixture is ideal solution, calculate the fugacity and coefficient for amino by using second variable coefficient. So second variable coefficient is this one. I feel like I don't really have to do much explanation. It's just a matter of plugging in formulas, because this is just 4 marks. Honestly, you can just, it's pretty trivial for me to really explain it really thoroughly. So yeah, I made a mistake here too, 0.99, and since they want an ideal solution and the mole fraction they give here is in gaseous state, so I have to 1 minus 0.7, which is 0.3. So 0.3, I'll get 0.2, 0.999 minus 1.07. So So it's actually just 0. Wait, what did I do here? Oh, times the pressure, which is 0.2. Wait, no. So if I want to find the fugacity, it's 1 minus y, which is 0.999 times 0.2 times 0.3, which is 0.99 times 0.2 times 0.3. I'll get 0.05994. Yeah, it should be correct. So that's it for question 2. Just have to familiarize yourself with the formulas. Pretty much that's it.